Hi, folks. Anthony asked me to talk about my notions on experimental design for a new project, and I'm happy to do so. I think a lot of what I'll be saying here is going to be pretty obvious to most of you. Some of it is very much my opinion, which I suspect many of you will disagree with. That's fine. I'd be happy to be there and discuss the points with you, but I'm in Manaus, Brazil right now, where, as you may know, the Amazon face experiment is moving forward. And there's a number of tasks that have to be completed by the end of the UK fiscal year, which is the end of this month. So, the UK government did announce at COP26 that they're going to be they are supporting the construction of the face infrastructure. This is a project that's been in planning stage for 10 years, more than 10 years now. The experiment will comprise 6 30-meter diameter face plots with elevated CO2 in 3 of them. The site's been well characterized. A lot of publications on different processes have come out of it. The construction of a pair of rings is starting immediately. The tenders for the contracts are in place, and we should be constructing the pair plots quickly with full implementation of the full experiment in late 2023. So this is pretty exciting, and that's why I'm not with you today. So I think first strong principle, I think, in putting together a science project is probably pretty obvious for everyone. It's start with the science question. Well, it's sometimes easier said than done, but I think it's best to try not to let site availability or technology drive the project. Rather take a more of a purist position and start with the science question, recognizing that that's not always possible. There's sometimes constraints. You must do an experiment here, or you want to do an experiment, want to try out a certain technology. And also, of course, some really important science questions may just not be amenable to experimentation. Do you abandon such questions? Perhaps, or maybe investigate contributing processes at a smaller scale. I think both are valid approaches. But I think it's important to put aside any notion that the experiment design represents a future reality. Recognize that in a decade or two, the vegetation, the soil, the interactive environmental conditions, all will be different and unknown. Therefore, it's really important, I think, to consider what you construct as an experimental system to test hypotheses. And therefore, a simplified system may be desirable. Regardless, the experiment really should have relevance at a larger scale or larger context. Now, I'm sure many of you have been in meetings with your institute's research director or whoever who insists that, our research must be transformational, outside the box research. We don't want any of that incremental research at our institute. Well, that reminds me of a lecture I heard from Hans Krebs when I was in grad school. The only thing I remember from his lecture is his statement that if you're not doing research that's going to lead to a Nobel Prize, it's not worth doing. Well, that's both an obnoxious and ludicrous comment, I think. And I say instead, hooray for incremental research. Now, I have to say that because I think it pretty much defines my whole career. And I'll use my experience with elevated CO2 research as an example of what I mean on that. So elevated CO2 studies over the many decades have gradually increased in scale and complexity, both in the biology, the level of biological integration we're looking at, and then the tools to investigate it. So we started, in the 1980s, I guess, with seedlings in pots in growth chambers, tree seedlings, and relatively short-term experiments up to 40 weeks, which is considered long-term at the time. But our questions, nevertheless, had a larger scale focus. That is, would nutrient limitation preclude a growth response to elevated CO2? And then what are some of the below ground root soil processes that could alleviate nutrient limitations. So a series of experiments, I think we answered some of those questions, but left on the table a number of really critical processes on tree growth and forest development, like what happens in the next year after winter dormancy and spring regrowth. And then the interactions with all of the other factors in the environment, temperature, water and rain and so on. And then since we're emphasizing below ground responses, it's really hard to represent that appropriately in a pot. So move to open top chamber experiments with tree seedlings, saplings planted in the ground, exposed for 3-4 years. And of course, this was done in a number of different locations. And, those experiments, I think, answered a lot of the questions from the growth chamber phase. That is, most of the responses were maintained over multiple years. But they also emphasize some critical uncertainties. That is, they really emphasize the importance, for example, of leaf area development. But leaf area development in an exponentially growing tree stand is going to be very different from the leaf control once the stand reaches a closed canopy. So that led to really needing to move to a face experiment. And the face experiments were very much designed around hypotheses and questions that developed from the OTC experiments. And then as the face experiments came to completion, first we instituted the face model data synthesis activity, synthesized a number of those responses and explored them in modeling context. We learned in the process that the primary responses to elevated CO2 are basically simple and robust. And then everything of consequence that we measure and compare across systems refers to the flow of carbon through the ecosystem, which pools it accumulates in and for how long, that is allocation and turnover, and then how those pools and fluxes interact with other biological and physical constraints. The face experiments emphasize the importance of time, that is forest development over time, carbon partitioning or allocation, nitrogen dynamics, other interactions with nutrient, and plant community composition. The model comparisons really identified important mismatches between models and data, and the processes for which more data are needed, which are illustrated in this figure that I won't talk about now, but you might want to explore it as part of your discussion. So that the modeling and the experience from the first generation of face experiments has informed development of a second generation, which can put to use, really create the opportunity to put these concepts of model experiment interaction to use by generating hypotheses and guiding experimental design, and then optimizing experimental data collection and use. So in this paper, we identified 4 experiments. That is the Uke face experiment in Australia, the By4 face experiment in the UK. Oops, that's Amazon face experiment in Brazil, the By4 experiment in the UK, and Swede face in Boreal system, which has not been implemented. But this greatly expands the ecological, geographical, and climatic range of the inference sphere of forest responses to elevated CO2. And there's a number of cross-site topics that can be approached here. That includes responses of mature forests, biodiversity, interactions with nutrient limitations, water stress, and temperature, which really were not possible in the first set of temperate forest experiments. So that's an example of this long development of moving upscale, answering questions, posing new questions to address at the next larger scale. And I think that's a good way to design science in general. it might be, and that's probably part of the consideration here on when you start thinking about a new experiment on the effect of this on that. Don't you hate it when titles of papers take that form? But I do. But anyway, this here means, of course, the global change factor: CO2, warming, moisture, precipitation, ozone, UVB. I don't know. Some of these factors are a lot easier to define than others. In fact, the examples I've given from CO2 might be hard to extend to all these others, because CO2 is a much easier factor to talk about. Otherwise, we're talking about averages versus extremes, say in temperature or drought, precipitation, the inherent confounding of temperature and humidity. If the interest is in disturbances, well, they're inherently episodic and unpredictable. A discussion that always comes up here is whether experiments should be single factor or multi-factor. Now, I know the argument, it's a multi-factor world out there, but to me, that does not mean that you need a multi-factor experiment, which I think often create confusing or one-off results. And I think instead, long-term experiments will naturally incorporate environmental interactions in a way that can be even more informative. So I guess that's perhaps heresy, but I'm an advocate for single-factor experiments. Now, there's also, really have to consider the various trade-offs in number of treatments, number of treatment levels, number of replicates, plot size, and so on. And that's regardless of level of funding. And we've seen the argument, well, we only could have 3 replicates because we didn't have enough funding for more. But with more funding, maybe you instead increase the number of treatments rather than the number of replicates, or the size of your plots, and so on. So those trade-offs are really important. And I think getting an idea of your statistical power and variation, sources of variation can be really helpful in designing this experiment. I like generating fake data and then analyzing just to see what system would work out best. I guess there's more formal ways of doing that. But okay, now the that of this experiment of effect of this on that is what ecosystem of interest. Well, there's of course strong a priori reasons to predict which systems are going to be most sensitive or most important. And there's been a lot of studies and reports written on that, so I don't really need to dwell on it. But I presume you'll want to take a look at those discussions. As I said before, I think a simplified system may be desirable, and recognize that site variability can really overwhelm your results. I've seen that in the Birmingham face experiment. A much more realistic forest, you might say, than the plantation forest we dealt with before, but the scale of the variability is beyond that of the plots, and it's really going to be difficult to detect responses because of that. Changes in plant community composition could be a really important part of the response of the ecosystem of interest, and really important questions related to that. Now, some of those questions are inherently long-term, such as change in tree composition in a forest, and therefore beyond the reach of an experiment. Although you can imagine discussing or approaching some of that with differences in seedling establishment and so on. But if the treatment causes a change in community composition, this really becomes a new and confounding treatment. We saw that a lot in the Occam experiment we did, a constructed old field system with 7 different species. Well, in responding to warming, soil moisture, and CO2. So we have started with a 3-factor experiment. But one of the species, Lespedeza, really took off, especially in, I think, in certain treatments. And then that really dominated the responses of that community going forward. So, I think if community composition is a primary question of interest, maybe it's best to think of a number of short-term experiments, so you're not just looking at the continued response of the trajectory of that new community that's created by the treatment. Modeling from the start. I think everyone here is strongly behind these notions that models are required for addressing the long-term and regional scale questions. Really need the communication between the empiricists and the modelers really early on in the planning process, which of course is exactly what you're doing. Identifying key uncertainties, and that figure from Belinda's paper is perhaps useful there, even if it's not all specific to elevated CO2 responses, I don't think. Using models to generate testable hypotheses. And then, of course, doing this really ensures that you're collecting critical data. That's something that we realized in the FACE model data synthesis activity, where the modeling didn't start till after we were basically done, and said, boy, I really wish we had measured this such and such. There are a number of other experimental design considerations. Well, I guess this is the third time I've said simplified ecosystems may be desirable because you can reduce the variability, so critical processes are revealed. And again, recognize that you're considered to be an experimental system for testing hypotheses, not a reflection of a future reality. Pre-treatment data are absolutely essential. I think every kind of experiment we talk about usually is very low replicated. And that really increases the importance of time series. So you can see the perturbation from a baseline in your treatment plots versus your non-treated plots. There's always pressure to start the experiment as soon as all the technology, all the engineering is ready. People are ready to go with it. But at the end of the experiment, I think everyone wishes they had more pre-treatment data. So it's good to try to resist the temptation to start too early. Despite wanting to start, really base things on the science questions, you really have to evaluate different exposure technologies. Recognize that some questions might be virtually impossible, even with unlimited funding, such as a free air warming experiment, large-scale free air warming experiment. Every engineering approach has a balance between realism and artifacts. Spatial scale and replication are really key considerations with regard to the not just science question, but also the technology. Because after all, construction and operating costs can overwhelm all of your other considerations. So I wasn't really going to enter in the discussion of what comes next, but I decided to put onto the table my candidate, and that would be a FACE experiment in a dry tropical forest. Why? Well, of course, we know the tropics in general are of overwhelming importance to carbon, water, and energy flows in the Earth system. And we're not going to be able, I'm really glad to see Amazon FACE moving forward, but we're not going to be able to address CO2 responses of the entire tropics based on it. A dry forest experiment would make a great comparison with Amazon FACE. Interactions with water are clearly important in this system. And I think the dry forest could be probably tractable with regard to the stature of the system, its complexity and infrastructure. It could also be done in the US, that is in, let's say, at the Puerto Rico NEON site. And finally, I would say, I hope we haven't abandoned elevated CO2 as an issue. The notion that we've done that, we've been there, done that, especially considering that, the investment that the US, DOE and the US has made in developing the technology and the science around it will maybe be left behind as the UK and the German governments take up the banner instead. So here's some pictures of the dry forest in Puerto Rico, and I will end it with that. Be happy to answer questions. I don't know if I'm online right now, but otherwise, send me emails or comments, and I'll see if I can address them. Okay, thanks. Have a good meeting.